slowly. The first thing which I want to do, I want to make a little change in terminology. So it was just inconvenient to say C structure with an additional structure or something like that, or C structure is a category with an additional structure. So I'm suggesting the following thing. So I suggest that what we call C structures will be called C systems. I actually Googled the word structure and synonyms to it. And one of the synonyms to structure was system. So I figured that we'll call them C systems. So a C system, so definition, a C system is a set level category with additional structure which we have described before. Now we also, as was already done in the previous lecture, introduced the notion of a B system. And B system is a collection of sets Bn plus 1 tilde with a B structure on this set, i.e. with the following data. And that we also discussed previously. So I'm just kind of fixing a more consistent terminology here. So we'll keep the word structure for structure on something, and we'll use the word system for this something together with the structure on it. So that was terminological point. So I'll recall once again now in a very short way what we have discussed previously, and we had theme 1 definition and properties, well, very little properties, but nevertheless, of C systems. We had theme 2 definition, partial definition of B systems. And pre-theorem that theory of B systems is equivalent to the theory of C systems. And this pre-theorem is what Peter and Chris are now working on formalizing. Theme 3 was monads associated to systems of expressions with free and bound variables. Let's see how and I guess theme 4, the reason I'm kind of calling them themes as opposed to sections or something is because in each of the themes there is much more to be said, and some of the things which haven't been said or I haven't worked on them yet. So in each theme the stuff can be much extended. We'll actually go back to theme 1 in future lectures when we'll speak about C structures with C systems with additional structures on them, like pi structure or stuff like this. So it will actually belong to theme 1, but we'll go back to it in later lectures. So theme 2 was type systems over a monad. And we have discussed several things there. We discussed our B structure associated to a monad, to a finitary monad on sets, to be precise. We discussed the free definition of a free type system over a monad as B substructure B subsystem, excuse me, subsystem in. So we had B system. So that's one of the reasons I want to repeat this, so that I learn to say things right. So B system associated to a monad, B system B of S associated to a monad S. And then free type system over a monad S is defined as a B subsystem in BB of S. And then we further had, let's see where to, maybe here. So we also had a definition of a, and that was the last lecture. Last lecture was a definition of a general type system over a monad S. And I will now recall this definition, not in complete detail, of course. So the definition was as follows. So definition, a type system T over a finitary monad S on sets is a collection of 4 families of subsets and we called them Bn, well, of T, but I don't always write of T. So let me just write a type system T equals Bn plus 1 tilde Bx n plus 1 and Bx tilde n plus 1 over a finitary monad S on sets is a collection of 4 families of subsets. So Bn in, and that I need to have a look at, not to make a mistake. In the product I equals 0 to n minus 1, S of the finite set 1 to I, Bn plus 1 tilde is a subset product I equals 0 to n, I suppose, if it's n plus 1. S1 I, or still n plus. Well, that we can check later. The syntheses are always a little confusing. Times S1n square. Now I need some space here, so let's say B EQ n plus 1, probably without tilde first, is a subset in product I equals 0 to n minus 1. It's the same thing as here, but it's a different, totally different subset. And finally, D EQ n plus 1 tilde is a subset, starts with the same product. And then goes three expressions, or as I would call them expressions, three expressions in variables from 1 to n. So we will use in our in my lecture, I'll use the standard notation. So if I have gamma, which is T1, T n minus 1, excuse me. It's actually 1 to n. If you don't mind, it's the same. So T1 is going to be S of the empty set. T2 is going to be S of 1, and so on. That's a matter. Instead, I could have written here. It's the same anyway. So, excuse me. Factor. It's just for the context. This has a context. These are typing judgments. These are type equality judgments. These are term equality judgments. And that's precisely what I'm going to say. So for gamma of this form, I'll write this, which means gamma belongs to Bn. So this is just a notation for this. And also, this is a notation for this is also, well, let me add something here. So gamma T type is a notation for gamma T is well formed. Gamma turnstile OT is a notation for gamma OT belongs to Bn plus 1 tilde. Now gamma turnstile T1 equals T2 is a notation for gamma T1 T2 belongs to B EQ n plus 1. With the indices, there might be some. And finally, gamma O1 equals O2 column T is a notation for gamma O1 O2 T belongs to B EQ n plus 1 tilde. So having said this, so a type system, blah, 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 over a finitary monad is a collection of subsets satisfying the following conditions. And I'm going to write these conditions for now as follows. So the first group condition says that Bn of t, B tilde n plus 1 of t is a B subsystem of B of S. And by the way, this thing is exactly Bn of S, and this thing is exactly Bn plus 1 tilde of S. And then there is I'll just write many conditions on BEQ and BEQ tilde. See the text, so see expressions current. Or notes from the last lecture. Now, what I want to formulate. That's where we stopped last lecture. Now, the first thing is a theorem, which I didn't. I probably need to start with a definition or two, and then I'll give a theorem. Right. So now if I have a type system, I still need to have, I want to associate to it a B structure, which is not directly, I mean, I cannot, there is a B structure which is just defined by these two things, but I want this thing to figure in the definition of the syntactic category of a type system or in the B structure of a type system. There seem to be some kind of, is everything understandable, or are there any questions? Okay. So I'll start by defining something, I'll call it QBN, which means Bn quotient. So a quotient of Bn. And it will be Bn over an equivalence relation where 0 is identity on the one-point set, because B0 is one-point set. And equivalence n plus 1 is defined by the condition that gamma is n plus, let me say, gamma t is equivalent to gamma n plus 1 equivalent to gamma prime t prime if gamma is n equivalent to gamma prime and gamma t equals t prime. So in other words, gamma t prime belongs to B n plus 1 EQ. And we also have Q B tilde n plus 1 equals B n plus 1 tilde over an equivalence relation where gamma OT is n plus 1 equivalent to gamma prime O prime T prime if gamma is n equivalent to gamma prime and gamma O equals O prime in T. So this gives us definition of this set. Yes, sorry, I probably need to write it slightly different. You're right. T is n plus 1 equivalent to gamma T prime. Yeah. So the theorem, there exists a unique B structure on the collection of sets QBN plus 1 tilde such that the projections Bn plus 1 tilde, the projection, I suppose, QBn plus 1 tilde is a homomorphism of B systems. So this is that's a theorem, pre-theorem. Well, it's almost proved in the text, so it's close to a theorem, but we'll need to formalize it also. And then I can also say a definition. So if I have a type system in the sense of this definition, then its syntactic category is the category which underlies the C system associated to this B system. So we know that C systems are the same as B systems. They're equivalent theories. So to this B system, I can associate a C system, which will be a category with an additional structure. And this category is called the syntactic category of the type system. Now, excuse me. Steve has mentioned in his lecture on univalent foundations, right, the day before yesterday, that the more usual approach to definition of type system is through the inference rules. So I want to give an example. I haven't kind of spelled it out very carefully before the talk, so I may have to think during the presentation. But I want to start, so I'll erase all this, and I'll start with a usual inference presentation of a type system, which will be our example of a type system. And then I'll explain how it translates into this language. And the translation will be very, very direct. So the type system which I want to use as an example will be the logical framework. So I'll start with the logical framework as an example of a type system and show how it translates into this language. So let's see, what do we need from here? Probably nothing. Bob will correct me if I present the logical framework wrongly. So let's start writing this in the usual format. So gamma is usually an abbreviation for a context. So I guess here are the derivation rules. Let's so from nothing, I can derive how does one start? Okay, one starts like this. That's right. So from nothing, I can derive that they are actually, in my notation, it will be like this. That's the first rule. Now, I want to say that given a context gamma, I can add to it I want to write this down, gamma X type. Now, this is assuming that this capital X hasn't appeared in gamma before. And this thing which is called type is kind of the only universe which exists in the logical framework. The logical framework has only one universe, and this universe is called type. Actually, it's with a little t, right? I mean, the classical. Yeah. Okay. Good. Little t will be better. Okay. Now the next thing is gamma xt gamma prime implies gamma little xt gamma prime x in t. There is this rule. Now, presumably need a rule gamma turnstile capital X type gamma little x and capital X like this. That just, well, in TS, of course, there would be some EL here occurring, but here they don't use EL, so it's a little messed up. Oh, we defined this. You don't have variable types? Okay. So let me just put this one here then. Capital X is an expression now. Well, it might be a variable. Well, it cannot be, but it could have been a variable, but it's not. So then there is a derivation rule of the form gamma x1, or let's say xt t prime type. Right? This t? Oh, you need to say that it's in a little type? Doesn't it follow from the rest of the rule? And then that implies that the product xt t prime is a type. So we'll say is a type is one thing, as is in type is another thing. So is in type is a stronger thing than is a type. Because little type itself is a type, but it's not in itself. It's a little. Huh? Can big T be a big type?
I mean, you have a special type.
Yes. But there is no way it can happen to be on the left hand. It just cannot occur in the context. There is no rule which would let it to occur in the context, if I understand correctly. Yeah.
In the second rule where it says x colon type, perhaps we don't need colon there. Because that's what's confusing us into thinking that x is a certain type.
That's what it is. How else? Then you would need EL. there is a substantial distinction between uppercase type and lowercase type. Well, that's purely a notation.
Yeah, that's what I mean.
That's okay.
But it's what you can say to this.
Yes. So I can probably write here is type. Yeah. Or so I need also to say given a list of variable names which I used, which we call in TS FV capital, the rules for LF of FV, so to speak, are as follows, right? But they're given, but this thing is a type. Actually, right. So let's. Well, we also need this of. But you don't want to move. Well, how do you work with that? You don't want you don't want to move this little type to the left. So it's. Okay, so I'm sorry for doing this during the talk, but so maybe you can. So what is going to be FV in that? And FV is probably called sigma. Empty. I don't know how to write empty. To be what?
Sigma with a constant declared colon type B.
Like the colon.
Like C colon C. Easier than dictating. Yeah. So the usual setup is this. Sigma can be, you say empty, or sigma and you declare C being T, or sigma and C being, and now there's a special thing called K, which is a kind.
Okay.
So this is the object, so to speak, and these are the type families, so to speak. These are the basic ones. These are the constants that generate everything else. If you want to, maybe I should use a different letter, capital C or something like that. Okay. So the idea is.
What is K?
So the idea is that
is a name
you would want to be able to introduce, for example, you might have like in pair setting, you might have a type of sets. And you might have a family of types indexed by sets. So you'd say this. So in pairs terminology now, we're often called types or called sets. So the idea is we'll say we have a type of sets, and then for each set we have a type of the elements of that set. Okay, so that's the.
Wait. So K has its own syntax.
So K, I have to tell you what K is, right?
Okay.
Okay. And so what are the.
And what is T? And T is just a name.
Type is going to be something which is classified by the kind type. So there are two kinds. There's the kind type, which is the basic one, and then there's pi, x, and a, k. And a special case of that is a arrow k. So I'm using the special,
Okay.
case of it here. So in this case, set is a particular type, so I can form a family of types indexed by sets. Okay, I mean, we could have called those anything, but to be suggestive. And then this is, so that would be an instance of that. So the basic thing that you have to start out with is when you look at the kinds, you end up saying, I think in your notation, you end up saying type is a kind, as a type, and you have a family of times, then pi x and xk is itself a kind.
Okay, I know what I need to do.
Okay, so this generates the kinds that you need in order to specify the constants, which is what you need to say what are the base families. And then the apparatus you have makes perfect sense because I need some rules for the constants, but apart from that, once I know what the kinds are, then I can get things of kind type. And that's the reason why it has to be colon, because this capital X could be a constant applied to a term.
Wait, Bob. I think let me do the following. I understood my mistake, and the mistake was that I didn't understand logical framework well enough to present it right now. So I will backtrack. I will do it next time when I learn it, and I'll follow the other line which I have prepared better. So no. We'll do it other way around. I'll learn from. I'll look at a paper, and next time I will. So that will be my my task for the next lecture to actually do it well. And so I'll just do it well next lecture. And this lecture then we'll do the other part. So what I was going to do, I was going to give an example, which I kind of failed in, but give example or a family of examples of how one creates B structure from a syntactic data. I'll do it next time. So instead, I will continue following the kind of the flow of the material in the paper, and instead of showing how to get a B structure from syntactic data, I'll show how to get a C structure from C system. Thank you. C system from a category, usual category, level 3 category, not set level category, with a universe. So that will be actually sim number 6. C systems arising from categories with universes. We'll start with definition. Let kind of round C be a category. A universe in C is a collection of data of the form first, it's a morphism. Well, I should have said two objects in the morphism, but the morphism is kind of easier. U tilde to U. And second, for each f from an object of this category to U, a pullback square of the form x f u p u tilde, and this particular pullback, which is a chosen pullback, will be denoted x comma f. And this upper thing is called q capital of f. And this lower thing is called p sub xf, this vertical thing. So that's what I call a universe. So a universe is a choice of a morphism. No, I mean the honest category, category up to an equivalence.
I don't know what the difference is.
Well, in set theoretic mathematics, there is none, because set theoretic mathematics is not equipped to define what an honest category is.
So, what mathematics is
Well, what it means is that, well, from set theoretic point of view, it means that all the constructions I'm allowed to do with C will have to be invariant under equivalence of C, under equivalence of categories. So I'll have to keep track that everything I do is makes sense when I replace C by an equivalent one. As opposed to set level categories, where all the definitions would just totally fall apart if I was looking at things up to an equivalence. Well, actually, I'll have a theorem which will underlie this particular issue, and I'll have the theorem very soon. So,
This already naming the fullback seems like something.
well, it's a choice. No, it's an addition. It's a
Equivalent category, a category equivalent to C, and we wanted to transport the structure to the other category in some sensible way.
no. You know, you cannot transport the structure. Well,
So what was your comment?
the comment. No. You'll talk about equivalence of categories with universes. An equivalence of categories with universes will be something which takes into account this is an additional structure in a category. You can make additional structure like by choosing an object in a category. You can speak of a category with an object. Right.
Yeah, sure, but then I thought that if you had an inverse equivalent to C, then you can have problems from whatever point of view they were.
But that will be theorems that it's not going to be a problem. Or I mean, no, I mean it's just exactly the same thing. You can speak about a category with a distinguished object in it. Also, if you go by an equivalence and then come back, your object will be a different object. But you can define what is an equivalence or functor of categories with distinguished objects. It's a functor together with an isomorphism of the image of the object with the object in the other category. So in the same way, we'll define what is an equivalence of categories with universes. And then we'll show that everything is respectful of this notion. So so now construction. So let CP be category with a universe. So there are also these choices of fullbacks which I'm not writing in my notation. They're implicit in the notation, and it will be clear why they're implicit later. Be category with a universe, and PT a final or terminal object in C. So when I'm declaring it, I obviously assuming that it exists in particular. So we define, or we construct, better maybe say, we construct a C system which will be denoted C of round CP. Actually CC, excuse me. Was in the paper it was CC, as follows. So we need to start with ob of this CC of CP. And we'll have objects graded by natural numbers, as we'll need anyway. So I think I first need a notation. So here, notation. X, F1, and so on, Fn will be my notation for many parenthesis x comma f1 comma f2, many parentheses and things, fn. So what it means on a picture is that I have x goes by f1 here. X goes by f1 to u. I take the pullback, the chosen pullback. Then there is a function, then there is a morphism f2 from this pullback to u. And I take the chosen pullback, and it will be denoted. And its standard notation would be this, but I denote it for simplicity as x, f1, f2. And then this goes to u by f3 maybe, and I have a chosen pullback. It will be x, f1, f2, f3. So the object n will be the set of sequences f1, fn. Is that how I denoted it? Capital F, okay. Capital F1, capital Fn, where F1 is from the chosen terminal object to u, and Fn plus 1 is from point comma F1 Fn into u. I don't know. That's how it's in the paper. That's to keep the to keep things consistent with the paper. No. There was nothing. I don't quite know the reason for that. So what actually happens is one can draw it like this. Now, this is clearly a set. I mean, if objects of a category don't form a set, they form something of H level 3, as we know. This thing is definitely a set because it's just a set of it's some construction which starts with the set of sets of morphisms. So it's something which made out of sets, and it's a set. Now, morphisms from F1, Fn to G1, Gm will be defined as morphisms in the category C from this object point F1, Fn to the object point G1, Gm. Now, it's not difficult to see that if I forget that it's a set level category and consider it as a usual category. So set level category is a kind of more rigid, more informative object than a usual category. If I consider it as a usual category, then it will be equivalent to the full subcategory in my original category C, which consists of objects which can be obtained by iterated pullbacks from my morphism P. No, but if I consider it as a category up to an equivalence, then whether it's canonical or not stops being important. So it's equivalent. This category is equivalent to a category, to the full subcategory in the original category, which consists of objects which can be obtained by iterated pullbacks from our universe morphism P. So in applications, this morphism will be some sort of a universal morphism. So it will be almost the whole category. Now we need to define the rest of the structures which define a C system. And then we'll need to verify the axioms. So first of all, it's obvious that what we have is a set-level category, because associativity is obvious from here. It's just the associativity in the original category, and the unit is obvious, and it is obviously a category. And maybe I even want to formulate a lemma or a theorem here, which I will not formulate in great detail, but you can actually. No, I want to formulate it carefully. So let CP be a category. Consider two categories with universes, CP and C prime P prime. Be categories with universes. Let further F, well, let's say phi, C to C prime be a functor such that phi of P, think a second, let me look at the formulation here. Such that be a functor together with two morphisms one morphism will go from, if I take phi of u tilde in the first category and compare it to u tilde in the second, u tilde prime. So here I want to have morphism phi tilde, little phi tilde. It will be phi of P, phi of U, U prime, P prime, and phi without tilde, with two morphisms phi tilde phi, such that, well, let's see, it's morphisms or isomorphisms? Morphisms so far. Such that this square commutes. And assume that phi of point is a final object, and phi takes pullback squares to pullback squares. Then, well, actually this probably be lemma. Well, then phi tilde phi, phi, little phi tilde little phi, define a homomorphism of set level categories CCCP into CC C prime P prime. This is easy to verify. So I start with, so I want to have a map on objects. So for example, I have some kind of f, just the point going to u tilde. So this will be some kind of f1. That will be the pullback. So I want to assign to it a map from phi of the point to, excuse me, from point prime to u prime. So first of all, I know that phi of the point is a final object, so there is a unique isomorphism between this final object and pt prime. Second of all, I have a map from phi of pt into, second of all, excuse me, I have a map from u prime to, how does it work? Here. So I want to get this. I have this. I apply phi to this. Here I have little phi tilde to u tilde prime. Here I have phi to u prime of p prime. And here I have pt prime, a unique isomorphism between two final objects. So as a result, I get a map from the final object in the target category to u prime. So that inductively defines a mapping from objects of this set level category to objects of this set level category. Now, if now that may be kind of theorem 1 or construction 1, and then theorem 2 is if phi is an equivalence of categories, I don't need anything else, then let's denote it CC of phi. CC of phi is an isomorphism of set level categories. So that's basically what I meant, but I'll show what how this construction connects something which is up to an equivalence to something which is up to an isomorphism. So this construction starts with, thank you then, with a category with some little additional data on it, and produces another category, but the construction is such that an equivalence on the original categories induces isomorphism on the categories which are produced. So it lowers the level from 3 to 2. And the next lecture, I'll outline the rest of the C structure on this category, so that we'll get a construction which starts with something of H level 3, namely a usual category with a universe in this sense, and produces something of H level 2, namely the corresponding C system. Thank you.